Welcome back to lesson number 3 on chaos, fractals, and dynamics, based on Robert Devaney's little textbook on this. Remember, we're iterating on f of x equals x squared plus c. Let's go over what we learned in lesson 2. We learned that if you had a seed of 0, iterating on x squared plus c with c as the parameter. We learned that for c at 0.25, on to infinity, but not including 0.25, we get divergence, escapes. Between negative 0.75 and 0.25, you get eventual convergence. It's an eventual one cycle that's sometimes called. Of course, you get immediate convergence at c equals 0. At negative 0.75, we get a changeover, sometimes called a period doubling, because it becomes an eventual two cycle, and that goes on between negative 0.75 all the way to negative 1.25, although it changes over immediately at c equals negative 1. And at negative 0.75 and just below, you get an eventual four cycle. It's a little harder to see at negative 0.75 because it's so slow, but it does happen, and we're going to show you that a little more clearly today. And again, when you change over from a 2 cycle to a 4 cycle, or a 1 cycle to a 2 cycle, or a 4 cycle to an 8 cycle, it's called a bifurcation or a period doubling. And now we're going to take a look at this, and again we're going to be using the GeoGebra software, but it's a little bit different way of looking at it now. We're going to look at it with a sort of a histogram, and let me explain what's going on here. Down here, these are the values we're getting for the iteration. Those are the values that in the other program you would see in the spreadsheet, or we would list the last 4 on the main sheet. And now, instead of listing them like that, we're going to count how many times the same number occurs. And you say, well, the same number is not going to occur because it's almost always going to be a little different and out far in the decimals. And what we're doing is we're breaking it up into regions. So for instance, notice here we have c equals 0.25, and our delta c is 0.01. We're going to change 0.01 every time as we move this way. And down here, these are our c values. And this right here, you see where it's 0.5 on one side? Well, just to the left of that is going to be probably 0.49, 0.48. In other words, anything that goes in this region adds 1 to the count of how many times you've hit that number. It's not really a number, it's you're hitting in a region. So for instance, see right here, we hit, what's that, about 0.25 plus or minus a little bit? We only hit that once. That was one of the earlier, that was probably the first iteration. See, we started out here at 0. So 0 was 0 to probably 0.01. And gradually we moved here, and then we started getting the same number over and over again. It's not really the exact same number, but it's very, very close, and that way we can see if we're homing in on a number. Okay, so this will be easy to see as we change c. I want to take c and move it to the left, and remember, all of these to the right of 0.25 is a divergent. So see, it disappears. That's because we're not getting any of these numbers between 0 and 1.3 because it's getting big so fast. But here, see how we're getting down to a 1 cycle? And I don't remember how many times I'm doing this, but it's probably 1,000 or a couple of thousand. And so we're just going to keep on moving that c to the left. Now remember, at 0, how it settled down immediately. Well, watch, see, as we get close to 0, see how it's settling down very, very rapidly? That's not surprising. That's what we saw with the other software. That's what you would see on your calculator as well. And right here, it settles down immediately. And now we move left, and we keep on getting a 1 cycle. We're getting the same number over and over again with our thousands of iterations. Probably about 1,000 iterations. I'll have to look that up. And here we go. Remember where it changes over? At negative 0.25, negative 0.24, negative 0.25. Okay? I'm sorry, negative 0.75. So we keep moving, still got a 1 cycle, Still got a 1 cycle. It's taking a little longer to settle down, but really fairly quickly. Now it's really slow. It's taking a while. Here's negative 0.73. Negative 0.74. It takes quite a while to settle down. That's why we're getting some results that are not quite in our region. The region that contains the number that we're approaching asymptotically. Now we go to negative 0.75, and you can see there it does bifurcate. We are getting two different values eventually. It takes quite a while. And as we move left, it continues to bifurcate. An interesting thing here that we probably didn't notice when we're doing with the other software is the bifurcations get further apart. Okay, negative 0.8, negative, and so on. I think it was negative 1 that it actually settled down immediately. Remember that? And notice it's settling down real fast now, and at negative 1 it should settle down immediately. So all we should see would be 2 lines. There we go. And the next big change we found came at negative 1.25. So let's cruise on over to there. Getting close. It's going to bifurcate right now, but it's hard to see because we don't have enough iterations to really see it. But boy, negative 1.26, it's obvious. And as we move, we'll continue to see a 4 cycle. Continue to see the 4 cycle. Right around there, not sure exactly where. It changes over. It looks like right there we either have an 8th cycle or we've almost got one, and now we really do have 1, 2, 3, 4. We have an 8th cycle, an eventual 8th cycle at negative 1.39. Remember, we're only doing this to the nearest hundredth on C, so we're not going to find the precise point with this program. We'd have to calculate it. I'll show you how to do those calculations later on. They are a little tedious. There's something you can skip over, unless you really want to do it, which I hope you do. We keep going. Now it gets interesting. What's going on here? Well, when we get to negative 1.42, unless we're doing a whole lot of iterations and we're keeping very close track to a number of decimal places as to what's going on, it's very difficult to tell how many cycles we have. And at some point, the number of cycles is approaching infinity. And that's going to occur in various places, and it'll be doing that for a while, like here at negative 1.47. It's very, very difficult to tell what's happening there. And then negative 1.48, we're back to something that has a pattern to it. This one is 1, 2, 3. This has six places that we're approaching. So it's a eventual 6th cycle, which means somewhere soon after we're probably going to see something like an eventual 12 cycle. And it can be proven that there are, and I couldn't prove it, that all possible integers for positive integers for cycles exist, from a 1 cycle up to any number you want. So here we're at negative 1.5, and clearly we get into the region that would be called chaotic, simply because we can't predict. If we have one number coming up, we can't predict the next one very well, or at all. And that's chaotic behavior, and that's really chaotic now. We're not homing in on any particular number. Now what that means will come about, ooh, look at that, negative 1.63. We're suddenly back into a region where there is a pattern. And then just as quickly, negative 1.64, we're back into a very chaotic region. And we keep on going. Look at that, negative 1.79. I would think that is chaotic, and yet there's some pattern to the chaos. There are some numbers that never come up. Okay, we're back to another not-so-chaotic region. Chaotic. And we keep on going. And we go all the way to negative 1.2. And once we hit negative 1.2, negative 2, right before that we're in a chaotic region. If you hit negative 2, because you've got x squared minus 2, when you plug in 0, you get negative 2. When you square it, you get 4 minus 2, you get 2, and it escapes. So and you can play with this in your calculator to see any number for C that you put in, -2 or less, you're going to escape. Just like any number greater than 0.25, you're going to escape. So all of the interesting dynamics for us occurs between -2 and 0.25. That's the area of real numbers that we're going to be interested in to see the pattern of behavior. Let's see the whole thing go through in one fell swoop. We're moving from -2 all the way to about 0.3. Chaos there, a break from chaos, and so on. Notice how by doing a histogram we can cover the entire region from -2 to 0.25, figure out pretty much what's going on without having to worry about looking at a list of numbers. Okay, that's a very powerful way of looking at things in a graphical manner instead of just studying the numbers, looking for general patterns that are sometimes concealed by the specific numbers. We're just cruising left to right. We're now up to -1.25, 2 cycle there. Okay, and we're going to find a 1 cycle changeover, and that's going to occur at -0.75, if I remember right. That's the boundary. Here we come, 2 cycle, 2 cycle. And here we go, 1 cycle. As we move to the right, we're going to speed it up a little bit. Get all the way over to 0.14, -0.14. Here we go. And when we hit 0.25, beyond 0.25, instead of converging to a 1 cycle, we get divergence just like that. Okay. So let's see what we've learned today. All right. What we've learned today is that so here is what happened today. In today's lesson, we used a histogram to examine the dynamic behavior of the iteration on f of x equals x squared plus c, and we let the parameter c vary over the reals. Let's summarize what we learned. On the interval -2 to 0.25, not including those numbers, as c values, the orbit does not escape. It does other things, but it remains bounded. It does a lot of different things. Outside of those regions, outside of 2 and -2, with those as c values, the orbit escapes, it diverges. That won't be nearly as interesting to us as the region where it remains bounded. In this non-escape interval, all sorts of things happen. All possible eventual cycles occur, from a 1 cycle to a 1,000,000 cycle to beyond that. The behavior remains the same over some interval, then there'll be a sudden change in the number of cycles, and that's often associated with a bifurcation or a period doubling. There are regions where we can't determine any cyclic behavior. These will be called chaotic intervals, where behavior becomes unpredictable, and one of our goals is going to be to better understand what this really means. So I haven't really defined that yet. So next time we'll probably look at another way of seeing this graphically, involving a 2-dimensional diagram, and that'll be a pretty good visual way to see things, very dramatic. So in the meantime, go over what we've already done, play with it, and have time.